Welcome to Statistical Inference. In Lesson 1, we're going to look at simulations and sample means. We're going to explore the concepts of sample means, explore repeated sampling and its approximate normality if n is large, and summarize the general properties of a thing called a sampling distribution. Estimating population parameters. Population is the complete group from which you want information. Sample is part of the population. A random sample is a sample taken so that every member of the population has an equal chance of being selected. A parameter is a numerical characteristic of the population, such as the mean. A statistic is an estimate of a parameter from the values observations of a sample. A random variable is a variable with a numerical value that depends on the outcome of a chance event. These are usually represented with a capital letter. Sample means. Recall the mean of a sample is given by x bar being the sum of the scores divided by n, the number of scores. The standard deviation of a sample is denoted as S. Sampling variability. Any quantity computed from values in a sample is called a statistic. The observed value of a statistic will vary from sample to sample. This is referred to as sampling variability. Exploring sampling variability. Consider a small population consisting of 20 students. That's the whole population. You've got student 1 through 10, 11 through 20. Amount of money in dollars spent on takeaway food per month is shown in the table. This is the expenditure. For this population, mu is the sum of x divided by n, which is $99 per month. That's the population mean. Suppose we do not know the population mean, which is mu equals 99. We decide to estimate the population mean by taking a sample of 5 students. Is this reasonable? We will select 4 groups of 5 students as samples from the population. Here we're taking samples of size 5. Now, sample 1, 2, 3 and 4 are shown here, where really sample 1 was the first 5 students, the second 5 students was sample 2, etc., etc. The mean of those samples, which is x bar, is shown in red. So the sample mean of sample 1 is actually 15.8 above the population mean. Note sample 4 is 13 below the population mean. So those means of the samples vary dependent on the students that were in that sample. The variability of the sample means is shown in the third row. The value of x bar varies from one sample to the next. This is an example of sampling distribution, which is a distribution of sample means from many samples of the same size. Consider a sample of size n equals 14, and this sample intentionally is going to be the middle 14 students. The sum of those values divided by 14 is 101.4. Note, here we seem to get a sample mean, which is closer to the population mean, which was 99. X bar based on a large sample will tend to be closer to mu than x bar based on a small sample size. Sampling distribution of a sample mean. And the objective of a statistical investigation is to make an inference about the population mean mu. It's natural to consider a sample mean x bar as an estimate. First, we must study how sampling variability causes x bar to vary. Sample size n and characteristics of the population are important in determining properties of the sampling distribution of x bar. In this experiment, the original population x has an expected value of mu and a variance of sigma squared. Each sample has a mean given by x bar, so samples are given by x bar and the population mean is mu. The distribution of these means can be referred to as the following. Example 1. A research paper suggested the distribution of platelet volume is approximately normal with a population mean of 8.25 and a population standard deviation of sigma being 0.75. This will look like a normal curve with our center being the population mean of 8.25 and one standard deviation is 0.75. The next stage is completing samples of size n equals 5 or 10 or 20 or 30. Note the population mean was 8.25. So if we start with n equals 5, here is the distribution of our sample means. 8.25 is about here. Now, a lot of the time we're getting pretty close to our population mean, but other times our sample means, border on 9 or down to 7. there's a bit of variability in our sample means. This is the distribution of our sample means. If we have n equals 10, that means our sample sizes are getting bigger. We still have, a histogram that looks normal in a bell-shaped curve. Now we're centered around 8.25, which is the population mean. Notice we're not getting as many of our sample means, the extremities here at around the 9 and the 7 region. We're getting a bit tighter. If we have a sample size of 20, again, we're very close to 8.25 as our center, but the variability seems to be a lot less than when the samples were 5. You even go to 30 now, the variability in our sample means is smaller because, here we're not getting many even above 8.7 or below 7.8. Most of our scores, or sample means, are occurring pretty close to the population mean. X bar based on a large sample will tend to be closer to mu than X bar based on a small sample size. N is sufficiently large, the sampling distribution of X bar is well approximated by the normal curve. General properties of the sampling distribution, where sigma is known, note it will change when we don't know sigma, is that the sampling distribution of X bar is always centered at the mean of the population. A sample standard deviation is sigma divided by the square root of n. The spread of the sampling distribution of X bar decreases as n increases. The population distribution is normal. The sampling distribution of X bar is also normal. The central limit theorem. When n is sufficiently large, where n is greater than or equal to 30, the sampling distribution of X bar is well approximated by a normal curve. Suppose that a random sample of size 64 is to be selected from a population with mean 40 and standard deviation 5. Identify the mean. Here, the assumption is that the sample mean will be equivalent to the population mean. That is, it's going to be 40. The sample standard deviation would be population standard deviation sigma divided by the square root of n, which is 0.625. Example 3. Determine the approximate probability that X bar will be within 0.5 of the population mean. And note, before the mean was 40 and the standard deviation of a sample was 0.625. So calculate the Z scores. Note that I'm saying I want to be within 0.5. So that's 40.5, subtract the mean divided by the standard deviation. That's 0.8. So what I'm trying to work out is that my population will be within 0.5 of the population mean, which is a Z score of 0.8 either side of the mean. So Z scores range between negative 0.8 and 0.8. Calculation of that is the probability of Z being less than 0.8. Take the probability of Z being less than negative 0.8. That is 57.62% approximately. Hot dog manufacturer asserts that one of its brand of hot dogs has an average fat content of 18 grams, where the standard deviation is 1 gram. Calculate the probability that a sample of 36 hot dogs has an average fat content greater than 18.4 grams. So mean, we know our population mean is 18, so a sample would be 18 as well, assuming normality. We're looking at the probability that our sample is going to be greater than 18.4. So standard deviation is needed as well before we can work out a Z score. So a standard deviation of a sample is 1 over the square root of n, which is 0.1667 approximately. Calculate our Z score. 18.4, subtract our mean, divided by the sample standard deviation is 2.4. So state the probability region. We're going to be greater than the Z score of 2.4. Calculation, the probability of Z score being greater than 2.4 is 1 subtract the probability of Z being less than 2.4. That is a very small percentage here, not even 1%, 0.82%. Now, a bit of a summary here. We've got a sample versus our population. The notation for the number is usually small n and a capital N for population. The mean of a sample is the X bar, and population is mu. The standard deviation of a sample is S, whereas sigma is used for population, your Greek letters. That's the end of lesson 1. Next lesson, we're going to look at it more from a technology base. But to test your understanding, have a go at the following question.